All right, so hopefully you're having a good time. We have 2 sessions done, 3 more to go. So this is the energy session for those of you looking for advanced materials. Just in case, like you're on the right flight, right? Okay. I always wonder, I mean, you board a plane and say, this is a plane going to blah, blah, blah. I'm like, okay. It's like, gives me great pleasure to introduce Ram. Ram is IT Madras graduate, 1996, I'm told. 96. He's currently at EPRI, which is Electric Power Research Institute, and he's the moderator for this session on energy, and he'll introduce the other panelists and take it from. I forgot, most important thing. Ram apparently knew the train timetable by heart. Yeah, for which, apparently called Loco in IIT.
Yeah, well, I don't know why I was called that way. It could be for different reasons, but yes.
Interpretation left to people.
Left to people, right? So thank you, Karan. Thanks for the introduction. So, you know, when we were trying to put this together, right, we wanted to have a good mix of. I mean, it's become a big topic right now, right? We have had Greta Thunberg just take the sailing boat all the way from England over to New York for the UN Climate Summit. We know what's happening with the Climate Summit, and you know it's interesting. It's when I talk to my son, right? They are a lot more engaged in these topics of sustainability and climate change than I think we ever were, even in college, right? And so, for me, the inspiration for some of the work that we all do in this space is not just because we want to do it. It's not because it's just mentally interesting, but it's also because I think we are doing it for the future generations. And there is some very interesting work that's going on all around the world. The big goals, as we have seen the last 5-10 years, and being in California, you're exposed to it a lot, right? Like the state of California, for example, wants to go to a net zero carbon economy by 2045. Not just making renewables happen, not just cleaning up the power system, but it's like getting rid of carbon everywhere, right? Whether it's in buildings, whether it's in industry, whether it's in transportation. And they're not alone. New York wants to do that. You have countries in Europe wanting to do that. Everybody has a goal, UK, France, 2040, 2045, 2050. So these goals are all popping up all over the place. Corporations want to do that, right? So as we look at what's happening, right, the sea change that's happening the last, I would say just in the last 5 years, what it makes us think is, are we ready, right? Are we ready to make that change? Some of this, getting to 30%, 40%, yes, the technologies are there. We can do it. But getting to that 70%, 80%, 90%, we don't know how we are going to get there. And I think that's the importance of the work that needs to be done. As we look at our esteemed panelists, right? Some of them are working on some of these, what I call earth-changing technologies that are going to happen in the next 10, 15 years. And that requires vision, that requires great engineering knowledge, that requires a business model that needs to be developed. It might not be there today, but how are we going to develop those business models that can make this transformation happen, right? So that's I think the reason we wanted to set up a panel on what I call the hard-to-reach technologies. These are the transformative technologies that we think can, in the future, make decarbonization happen. These are the technologies that need to be done to be able to address all the impacts of climate change that can happen, right? So with that little intro, we call it climbing the mountain. That's because we are looking at these hard-to-do technologies. Not the easy ones, but the hard ones. Then of course we have another panel in the afternoon where we're going to be talking about how data and new realm of large data sets and big data can actually help us with making this transformation happen. So that's the way the energy session is set up. And in terms of the structure of the session, we are hoping the panelists will speak for about 10 to 12 minutes. And then maybe one or two moderated questions, but I think we'll probably go to the audience questions first, so that the audience has a chance to interact with the panelists, and then we'll get back to the moderated questions after that. So, with that introduction, right, we talk about decarbonizing energy. There's two pieces here. If it works, so there's generation, energy generation and storage. And when we think of energy generation and storage, yes, everybody knows renewables, there's lots of renewables going on. We have seen that market transform in the last 10 years. The cost of renewables have come down, it's happening everywhere. There is some research going on things like modular nuclear reactors, right? It's, again, low carbon energy generation. And then we have to think about storage. As we think about how are we going to get to this 80%, 90% renewable goals, right? Storage becomes very important. And we have Shankar Ramurthy, who's working on energy harbors. Really, really interesting company. Looking at storage, that's not just 1 or 2 hours for your batteries for cars or things like that, but seasonal storage. The wind doesn't blow all the time, right? The sun doesn't shine all the time. You could have 10 days when there's no renewable generation. How are we going to balance the grid? And Shankar is going to talk about that. Then we talk about how do we get carbon out of the usage of energy. And when we think about it, yes, EVs used to be exciting and interesting, but electric transportation has to go beyond EVs. So how many of you have heard the word, and I might not say this correctly, flat scam? Okay, so that's the new word. It's the, I think it's called the word of the year now, because it's called flight shame, right? Flat scam is flight shame in Swedish. It's about the fact that the carbon intensity of airplane flights is pretty soon going to be the highest intensity, highest carbon emitter, right? If we start doing what we're doing right now in buildings and the generation grid, that's going to be the biggest carbon emitter. And so Satya is going to talk about how we are going to address that with electric aviation, right? So again, these are all pieces to the puzzle. Then we have to look at how we are going to decarbonize our homes and buildings and look at the technologies that can do that. Venkat is the CTO of Bloom Energy, the pioneers of fuel cell technology. He's going to be talking about what they're doing moving forward, not just for buildings, but at the generation level. There's all these issues around how to use gas, how do you do carbon sequestration. And so Venkat is going to talk about the big picture with fuel cell technology. And finally, we come to buildings, right? How do we reduce energy use in buildings? And Dr. Meher Prasad from IITM, and I'll do a little bit longer intros when we introduce the speakers. He'll be talking about how are we going to get buildings to be both affordable and low carbon, which is where we need to go to be able to provide affordable housing for the 600 million people. Just a quick vision. This is kind of how we envision it. So if you look at it, this is how our future cities are going to be. Here's how the future communities are going to be. You can see where there's technology needs everywhere, right? There's needs for energy generation, there's needs for storage, there's need for building integrated PV, there's need for control systems, there's need for modular construction. So there's a ton of engineering, a ton of technology development that has to happen to get to this vision of smart communities, sustainable communities, resilient communities, zero carbon communities, right? And with that, I will invite our first speaker, Venkat. Venkat is the, as I mentioned before, he's the CTO of Bloom Energy. Venkat's been spearheading the development of solid oxide fuel cells for the last 15 years. He's a pioneer in the field. And Venkat has a PhD from Clarkson University. And with that, I just have to pull up the presentation. All right, and you're welcome to use this and I can scroll it.
Yeah, good morning or good afternoon, depending on the time. So, anyway, I'd like to give a brief introduction about Bloom first. I think the way the company started initially was just power generation. So we never talked about how it fits into the clean tech, and it kind of morphed into it over time. So, and now when the needs are there in terms of not necessarily producing power, you need to produce this in an eco-friendly way. it needs to be reaching everyone in an eco-friendly way. So the play field has changed over time. So I've been with Bloom for, I used to be called Ion America. I've been with Bloom for 16 years. I've seen the transformation in the entire industry. Where we initially thought, okay, I have to get cheap power, but now we've come quite a bit. So let's start with the vision of Bloom first. If you look at it, our mission is to make clean and reliable energy affordable for everyone in the world. That's a mission which we have started. It's getting more and more relevant now than when we started, right? When we started, we thought we can produce electricity at a cheap, that's okay. Now, clean, being renewable, all these things have to be factored in. Above all, we have to save the earth. So there's the moral and ethical responsibility that we have is not necessarily producing power. With that in mind, we actually developed the technology. We were not only developed the technology, we made it in a way, it's a kind of a platform which allows us to do all the integration that you're talking about. Whether you're talking about energy storage, whether it's talking about transmission, all the stuff can be done, factored in. So we fit right in the center of it. So let me explain a little bit about that. So if you go to the next slide. For those of you who don't know about Bloom, first and foremost, we essentially have gone away from these called traditional, right? The central generation of power to distributed generation of power. We have seen this transformation in every industry. Take computers, we went to mainframe to laptop. We take telephones, we got landline to cell phone. Similar way we do it. And the one nice thing we did is we actually created a power generator using natural gas in the first place. And over the years, we actually made it to work on biogas. The biogas we are talking about is a biogas as you get it, without even taking the CO2 out. We have to take some of the nasty stuff out. That's basically it. We can use it as a feedstock. While you're doing it, because we are using the solid oxide fuel cell, it inherently allows you to use hydrogen as it becomes available. That's the way the world is also changing from a renewable perspective. The main thing we did is we did not just the research in fuel cells. Take solid oxide fuel cell, it's been in existence for the last 50 years. The innovation we did is we packaged in such a way, it's modular, it's manufacturable. I'll go a little bit detail about this technology itself. And furthermore, by doing it, you have to get the most efficient power generators. That's what we achieved. So we have the largest, in terms of if you take a single pass conversion of natural gas, chemical energy to, or any gas, chemical energy to power, right? There's a net efficiency highest that we achieved. And then, primarily because the way the solid oxide fuel cell works, there's no NOx or SOx emission because there's no direct combustion. It's actually, this is kind of an oxidation through a wafer. I'll explain the technology. So we kind of avoid all the emissions piece of it. And furthermore, most importantly, over the innovation, when you take natural gas, internally it has to be reformed into fuel. That is reformed fuel which produces CO and H2. And the way we do it, we actually recycle the water back as a process. So in a sense, we essentially eliminate the use of water. That's pretty big. We all think solar doesn't need water, but you know what? You have to wash the panels, you need water. Right? If you take gas engines, you need water. So we eliminated the entire need for water. It's pretty big. And even in the US where the water is available in many places, but in California we don't have water scarcity. It's pretty big for the customers. And then the last piece of it is we have high reliability. We've been tested out in real situations where we have earthquakes, we got fires in California, and we got natural disaster. We essentially have gone through all of them. We are able to successfully power them. Primary reason being we are not connected to the grid, right? We are actually isolated in a place, and we have got to a high level of testing to make this product robust, so we can actually do it even when there's a natural disaster. And that's biggest one. Other thing, we are 24/7 baseload, so we're not backup generation. We become the primary power for all the applications. And grid is used as the backup. We can use storage, or you can integrate anything you want, but we are the primary power. That's how we operate. We operate 24/7. And furthermore, the way we operate is modular. Because of the modularity, there is no downtime or maintenance time. You go to the next slide. Many of you may know about solid oxide fuel cell. And basically, what we have is the substrate right in the middle. It's just the wafer, it's a ceramic piece. It's got a unique property. The unique property is it is able to conduct oxygen ions at high temperature. By virtue of doing it, it actually releases the electrons that gives you the electricity. There is no combustion, so there is no direct interaction of the air or the oxygen to the fuel. So by virtue of doing that, we eliminate all the combustion, we produce electricity. And because there are no moving parts, in other words, you're not going through a traditional way of burning it, then you got a mechanical divide, then you convert the electricity. Every piece of it, you lose a bit of efficiency. Since we are converting the chemical energy to electrical energy directly, we are the highest, we're able to achieve the highest efficiency. In terms of construction, we actually go through steps. We got cell, we stack them, we put in modules, and then we build the power plant at the end. So we have a scalability, and every module is 50 kilowatt, and you can go from 50 kilowatt all the way to 30. We already have implementation of 30 megawatts, no limitation. You can go all the way up. And also it gives you can build as you need. It's not like one day you have to decide and do everything. You can build as you need. If you look at the next slide, I give you classic ones. We are supporting data centers, and in Korea particularly, where the real estate is limited, we actually did the car park type of structure you see on the right. And that's the thing in Korea, South Korea, where you can stack it up as much as you want. So it allows you, gives you the flexibility going from small installation halls all the way to large power plant. Next one. So what is the main difference here is, if you think about traditional way of doing power generation, obviously you produce power, right? Then you have to transmit it, then you have substations, and finally come to you. You got all the wires sticking out, right? There's nothing like that for us. So we basically have on-site power generation. Because of the fact that we are 24/7, we have reliable power, we got the modularity attached to this, you can practically get away from using UPS, backup generators, all the stuff can be eliminated completely. So in essence, if you're looking at the reducing the CO2 emission or greenhouse gas emission by virtue of just removing the backup generation alone is pretty big for places like in India. For instance, if you look at the right-hand side, it's the actual operation curve for the Intel data center that we support. Before we actually implemented, they used to have outages every day. Every day they have to go and create the backup generation. After that, we became the primary load, pretty much eliminated it. So if you look at the power that is produced by Bloom, it's constant, and it actually supports the load, regardless of whether they exist or not. That's big, and they would still have backup generation. They originally thought they cannot run it down, but now over the years they realized that they absolutely can eliminate it. So this is a good news for India. We go to the next one. So where we are heading is, if you look at the space now, if you think about more towards decarbonization, right? Today we can go take natural gas as it exists, right? And you can convert that to electricity today, and that reduces the amount of emissions. So if you take the next step towards it, then what do? You can actually take the biogas, which already have programmed. We have proven the technology to operate fine on biogas, landfill gas, whether you've got animal or food waste, all of them can be utilized. Just now we have made an announcement. We had worked with Energy Power, who have been involved in producing biogas. We just had an announcement yesterday saying that we partnered with them to take a 4 megawatt installation in Maharashtra and just taking the biogas and producing for power. As we go further, I think people talk about renewable hydrogen. The one of the reasons we did not focus much about that is not because we cannot run the system, the availability of renewable hydrogen. Now I think there are more technologies coming up, more efficient way of producing hydrogen as they exist we can use the system, primarily because of the fact that we convert from chemical energy to electrical energy in the highest efficiency, which holds good even in the hydrogen framework. We can continue to run it wherever the hydrogen is available. It's available as a byproduct of a fat, or you have a technology that gives you the water dissociation to produce hydrogen, regardless of what it is, we can use it. The last piece that we are doing is, think about the anode and cathode I showed. Because there is no fuel, air-fuel mixing, we have the ability to produce CO2, which is clean. There's no mix at all. So traditionally, if you take your flue gas, the biggest challenge you have is you got your nitrogen and other mixes, then the dilution of CO2 is pretty high. And for you to go take the CO2 out, so you've got a few molecules to be taken out of the big thing, and that's the challenging part. For us, it's actually given because we do produce CO2, which is clean, there's no mix with air. So now we can suck it up and give it to any downstream. Again, this is not delivered as a product in the past, primarily because the technology taking it, the CO2 as it is captured. There's a captured part of it, there's a sequestration part of it. There's been a lot of debate going on how you do it. Now, it's slowly in US, they have studied different ways of doing it. Even if you go and store the CO2 underneath the ground, they have identified, they've done a large geological study to figure out where you would be sequestering. So that is going in full speed. So now if you fit right in there, so now you take the CO2. Yesterday, the last 3 days I've been working with Southern, which is a utility on the East Coast. They are interested in taking the CO2 and putting it in the ground. So I actually visited the site, they actually do it. So we're pretty simple. So now that we are doing it to end to end, now think about the following way. So you got your natural gas, you got the high efficiency, reduced the greenhouse gas emission, right, compared to conventional. The next level is you can use biogas, you become carbon neutral. Now you extend it further. Now you have a way of taking the CO2 out and put it in the ground. You actually create a negative emission. So that's the way we are approaching the decarbonization problem. The other part of it is, since we are set up in a way that we can not generally do a power generation, we can integrate it to any technology. For instance, we have applications where we integrated solar. Take Apple Campus too, I'll go some case studies. We actually have coexist fuel cell as the primary source, and we got also solar. We can take any storage. We have applications where we are doing the storage also. In other words, that you can create a microgrid environment, we become the primary source. The biggest challenge in the microgrid as it exists is you need a steady power, otherwise your supply and demand is not going to match, so we are right there. So if you go to the next one. So, what's our overall strategy? First and foremost, actually distributed power generation. That alone kind of avoids all the transmission losses. We got the paradigm shift from natural gas to biogas to hydrogen. We can fit in this framework. Furthermore, people ask, hey, you are 65% efficiency, what do you do with the rest of them, right? The rest of the heat. We never bothered about it because the heat integration is a pretty tough one to do. Now, fact of the matter is when you go, the tower, the thing that you got in South Korea, they all coming into the common plenum, we can recover that piece of heat too. So we got work done in making it a combined power generation with heat recovery also. We can produce pure carbon, CO2, greater than 99.5%. We have the ability to go into negative emission. And furthermore, there is an interesting paradigm shift. People have been working on lithium-ion batteries and the battery technology for storage. But if you look at the article that is written by a professor at Irvine, and he's saying, Jack Brower, he says if you think of a following way, if you have excess energy in some cases, you got two options to do. You store it in the lithium-ion batteries, or whether to use it to produce hydrogen and transport it, and that becomes a way of shifting, right, from one place to another. And we are right there. So he claims that the round-trip efficiency is pretty high. Don't ask me how he's done it, but the math shows that he can actually do a better efficiency with hydrogen production than going into the conventional way of doing other storage mechanisms. So we are there. And then we are fitting into the other piece of it. You talked about carbon-free building. Primarily because of no emissions, we improve it in terms of you take every building, if you have to take the overall CO2 emission, we are in better shape. Furthermore, other particulate and everything, SOx and everything go away, so we are fitting it right in there. And since we are always power on, it actually helps out a lot. Last bit is transportation. This has come to Bloom's attention. What we are doing in California is we have something called LCFS credit, which is basically, if you take biogas, you produce power, and the power is used for EV charging, the government gives you an incentive. So we already kicked off a program. We're going to be working with a company which is managing a digester. They are taking the animal waste in Fresno and Bakersfield area, and they will be tying with us. We'll use their biogas to produce electricity, which will be used for vehicle charging. So we have thought through the whole thing about decarbonization in a big way. I think we are right in the center of it. We have all the tools to be manipulated depending on the demand. So if you go to the last few slides, just to want to give a few use cases. This is the one in Utah. The basic thing is an eBay data center. Originally they wanted to design a tier 4 data center with UPS and with all the generators. They had a plan to do that. Then they actually did an independent study. They hired a third party to review our technology and found out we are actually better than the tier 4 data center in terms of reliability. So finally they decided to go with Bloom. So we became the primary power and Grid is the backup. The good news is there are instances where the entire state of Utah lost power. We were the only one powering the data center. There you have to look at the value proposition. Every millisecond translates into millions and billions of dollars. So we've been operating for the last 5 years. It's old technology. The other one is Apple, you all know. If you have time, you can go and visit them. We became the primary source. This is the one I was saying. It's like a microgrid. We coexist with battery storage, and also we coexist with solar. And the controller, the way it works out is we can actually flex it. This is very important in microgrid. People have been talking about microgrid. If you don't have a stable and round-the-clock base load generator, it becomes extremely complex because when you produce power, when you deliver it becomes difficult. Take a simple thing. If you have solar, right? Solar shines in the daytime. That's why the power demand is high. So the amount of energy that you can use it for storage purposes becomes difficult. Whereas we have an option, we can actually kind of charge the batteries at night and discharge as we do in places like Home Depot, for instance. And then the last bit is the Intel. And the story I told you is they also had demand. They had two problems. One, they have to run the generators every day, right? And they had power outages. Second part of it, for them to expand it, they had to go to BESCOM and build a substation. So they came to us. We became the primary source. It's been running from 2016. So we became the primary power. We parallel with not only with the grid, we also parallel with the generators in this case. So when the grid is off, we can parallel the generator too. Initially, they were a little worried about Bloom. So they actually kept running the generator height thing. Over time, they got the confidence. They practically brought down the load that's taken out of the generator. And this is actually running at 1/10 of the load that you can support. So now they're planning on removing the generator. So this is another case study. Next slide. So to conclude, I think from Bloom perspective, we've gone through the entire ecosystem where we fit in. I think we are in a pretty good place. Particularly, we believe in the different technologies we're going to be talking about today. We have a way of integrating with all of them to create the microgrid solution. The thing that I did not talk about is that on the right-hand side, if you see from a fuel perspective, we have a flexibility on starting with natural gas going to biogas, and also using hydrogen, we can also capture the CO2 coming out. So we got a holistic solution. More importantly, if you go back to the first slide where we showed about our vision, the way we see it, where we see it, you saw the map of the world where you see the bright spot, that's the current opportunity. Where you see the dark spot is where we need to focus because we're all getting accustomed to things in the urban world where we have electricity. When you go into cases where you don't have electricity, that's where we can make a big difference. So in yesterday's conference, when I was talking about CO2 sequestration and I had a bunch of people, one of the things that came up, even the press release we did for India with energy power, if you manage it well, if you have cows or anything like that, let's say 300 plus, we can get them manage these animal waste properly and produce biogas. You can produce anywhere between 200 to 250 watt per cow. So that may be enough for even sesame village in India. So I think it gives you a perspective of things where we can take it further. Let's stop here. Thank you.
We'll do maybe one question, one quick, okay.
Quick, is your company publicly traded?
Yes, it is.
One
Yeah.
more.
I have a question.
Don't look at the stock value today, but it'll get there.
I have a question related to your application or installations in the hydrocarbon sector. Have there been...
Can you speak louder? We can't hear you.
You use the mic, please. If you ask a question, there's a mic over here.
Hi, I'm Arunama, and my question is related to any of your installations or applications in the hydrocarbon sector, specifically in a refinery or petrochemical plant or manned or unmanned remote locations in a cross-country natural gas.
Yeah, it's a good point. We've thought about it. If you think about petrochemical industry, the only restriction we have in the hydrocarbons we start with methane. We can go up to propane. If you go beyond that, the way we operate it we cannot handle it. So you can take the lightnings that is coming out of any particular refinery, that you can certainly use it, but there is a limitation on how far you can go with the hydrocarbons. We are working with some petrochemical, particularly Valero and ExxonMobil and other people who actually want to use our system to power their own refineries. You can use their own gas, but there is a limitation on how far you can push.
Is there a limitation to the technology in terms of the specifications and the strict safety specifications that you have in a hydrocarbon world?
Yeah, there are everything just in a purely gas world, we had to go through a certification on UL on the safety side. So we had to get every one of them done, including the gas handling. When you bring in the pipe to the system, that have to have certain safety things to be incorporated. The one good thing is we are not at high pressure. That's a big thing. There's no retention of gas in our system. We operate at atmospheric pressure. That's a huge thing compared to any other technology where you have to pressurize your gas. That gives you some problem. For us, it's actually the flow through. So the retention of gas in the system is very low. So it's a lot easier to operate.
Okay, so thank you. At this point, I think we have to move to the next speaker. We are going to, hopefully we'll have some time at the end. Next speaker is Professor Satya from IIT Madras. Of course, you all listened to him the last session, so I'm not going to do a big intro, but you're going to talk about something interesting that you didn't talk about, right? The last session?
In fact, I did an unabashed advertisement for this precisely for that reason, that I didn't have a chance to talk about that. So the hat that I was wearing there was actually combustion, but it's kind of ironic that I'm moving off from combustion and what I'm doing in my research and technology development. That's what I get a chance to talk about. So thanks, Ram, for the particular opportunity.
Forward?
That's okay. Right. So, in fact, I think I want to pick up from where Venkat was talking about. So I have this concept that we're now talking about landline phones becoming cell phones and the grid power becoming like microgrid. In fact, I coined this term called defrastructure, which basically says that we shouldn't actually have to have very high infrastructure. We should go in the direction of actually dismantling that infrastructure and have distributed everything that becomes a defrastructure. So in that context, I always get really pained by actually having to go to an airport 2 or 3 hours ahead of time and go through the rigmarole of security checks and all of that. Is it possible for a plane to actually come and pick me up from my doorstep? Right? And that's exactly what has motivated me to do this. This particular year has been very wonderful because we have had the Israeli aviation company called Eviation, which has put out this electric aircraft, a 9-seater electric aircraft called Alice. So I thought I'd actually, it's a commuter aircraft that has now been unveiled earlier this year. So I just thought that this is not a pipe dream, this is actually fast becoming a reality. Since Ram was actually originally talking about clean tech, I wanted to, and then he did point out about what the Europeans are getting sensitized about aviation becoming the next big frontier for cleaning up the environment. I thought that we will actually bring up this particular slide. So this essentially shows, so the automobile industry will actually talk about something called well to wheel, which is starting from production all the way on to consumption. So we need to keep in mind what the production emissions are. And so this basically compares a Cirrus SR-22 general aviation existing aircraft and then see if it's possible to convert that to a electric 4-passenger aircraft. And there are these comparisons on what happens during operations versus what happens during production. Of course, during production, you have a little bit of emissions that are coming up, but for the electric EV aircraft, but the operations-wise, you have a 5,000 tons of CO2 that's coming out for the existing aircraft versus if you use, so the question essentially is if you now have EV, how are you actually charging your batteries, and are you emitting emissions during the charging, and if you have the US cycle of mix of energy that's available versus California, you are seeing that there are much smaller contributors to emissions that aircraft put out if you now go electric. So what is exactly the problem? So the problem essentially is the energy penalty. So this energy penalty is a much severe penalty in aviation when compared to automobiles. So here's this graph that basically compares again the Cirrus SR-22, which is a four-seater aircraft and its corresponding electric aviation counterpart. So the point essentially is if I have to actually have the same range for the aircraft, then the aircraft, so I need to be able to put in so much battery, because the battery does not really have the kind of energy densities that today. And so if I'm looking at a battery density of about 200 watt-hour per kilogram, you're looking at a aircraft weight of about 11,300 pounds, which may not even be possible for the aircraft to take off in order to actually give the reach that it wants, right? So there has been a general skepticism about this in the last several years, where basically people say that there is this huge hyperbolic curve, and you need to get to a floor of about floor that allows you to have at least about 400 watt-hour per kg, and that's not happening yet, is the point, but we expect that it can actually happen at 2025. I have a completely different take about this, and that will unravel pretty soon. But the point people have been saying is we are waiting for this messiah of a big energy density jump. Now, it's not about the batteries alone. This is a very quick presentation that gives you an overview of all the different components, which means that we need to worry about the motors, and NASA has done a marvelous job, and in a mid-range of power at let's say about the 1,000 kilowatt level, where they have developed motors which have a very high power to mass ratio. And so one of the things that we have to, so the first thing that we have to worry about aviation is we need to have a very good energy density for the batteries, which has to be upwards of 400 watt-hour per kg is what we talked about in the previous slide. But here we also have to have these motors to be pretty light. So there's lightweighting that's very, very important, and so there are significant developments that are being focused on electric motors from a lightweighting perspective for this purpose. So closer to home, where I belong in aerospace, is some kind of aerotech that's actually also being developed by NASA, which is what's called as distributed electric propulsion. So that we actually take advantage of the fact that electric propulsion is what's called a scale-free, which essentially means that we can now distribute a lot of small propellers along the wing with small motors, and you don't really have to have mechanical transmission from a big engine somewhere in the middle to a lot of different propellers across, but we can simply run wires, right? So which is a lot easier. Now, what it basically does is it changes the aerodynamics of the flow past the wing and actually enhances the lift that is produced from the wing. Now, if you now produce lift, if you now have a very enhanced lift, why do you need that enhanced lift? Because your weight of the aircraft is going to be the same, so you want to actually have only the lift that you want, which essentially allows us to shrink the wing size. So you don't necessarily shrink the wingspan, but you actually shrink what's called the wing chord, which is the width of the wing, and that now allows for us to have a lesser drag. And if I have a lesser drag, I can actually show that improving the lift and decreasing the drag, or the L over D ratio, can actually extend the range further from an aerodynamic point of view. Now, in addition, since my wing is becoming a lot sleeker, I can have a much better ride quality and gust sensitivity, because I don't have these large wing surfaces that a gust could actually come and shake the aircraft. Now, that is important because now we are beginning to talk about urban air mobility, and in urban air mobility, we are looking at actually having aircraft that will fly at much lower altitudes than the conventional general aviation aircraft, where gust becomes important. So typically, general aviation aircraft get past the or near the tropopause, where you don't really have too much of gust. You're actually getting past the clouds and so on. But when you're now looking at urban air mobility, where you will be picked up from your home front, you're probably looking at an altitude which is going to be gust prone, and this becomes very, very important. So these are developments that have been happening. So of course the aircraft that this is actually what's called the Maxwell X-56 experimental aircraft that NASA did work on, but and that's not a VTOL. But what's important for us if you want to now do urban air mobility is VTOL, and there are, and I'm pretty sure you have seen these pictures. So there are a lot of these kinds of developments that have been happening in the VTOL space. So some of these things are actually only VTOLs, like for example, Volocopter or EHang, or primarily VTOLs, but you also have these VTOL fixed wing hybrids like the Lilium. And this one actually is not a VTOL, it's a bigger aircraft, Zulumiro. So there are many of these electric aircraft that are actually being developed. So it's very important, it's very, very interesting to note that in the electric vehicle space and the ground transportation, we have people like Google trying to do autonomous aviation and so on, but autonomous vehicles and so on, but they're not the conventional automobile industry. You don't really see too many startups actually trying to come up with electric cars, because there is this industry that already exists that is actually taking on this job. But in the case of aerospace has been big. And we want to now try to reduce the size of aerospace, so most of these things that are actually coming up are startups. And so there's a huge push for startups to actually working on this. And even Boeing and Airbus are actually trying to get startups to do the job instead of doing this. So it's a very interesting space that's happening. Now, when you now talk about so the other thing that's also happening is when you now try to have this urban air mobility, you need to have a large other kind of infrastructure that comes up, which is unmanned autonomous traffic control and certification bodies, all of that stuff. So there's a lot of work that needs to be done, right? Just I think a point very similar to what Venkat said, with electric aviation, you're away from the vicissitudes of oil prices. You have a much more stable electric supply, which essentially means that the cost of your the distributed electric propulsion technology on the right-hand side comes down significantly, which I believe is very, very important in the Indian context, because so India is actually the largest aviation growth story happening for quite some time, and that's actually the conventional general aviation. But what the Indian government has done in the last 5 years is to get into what's called as regional air connectivity, which means that they are opening up a lot of small airports all around, and there are lots of these commuter airlines that are coming up. What I think is possible with electric aviation, when the cost floor actually comes down even further for operation and maintenance, is going to actually spawn. So since a lot of people are actually Indians, I think I can probably spin this little joke. I dream that we need to have like an airline that calls like some Sri Raghavendra Airlines or something like that. So it should be like a Tom, Dick and Harry kind of airlines. Everybody should be able to actually float an airline and run these things. So question is, what do we do at Madras? I have a quick few slides about it. So, I'm a professor, so I have to actually look like a professor. So, so the first thing I have to say is what I'm doing on teaching. So I believe, and I've checked this, I think I'm the first one to actually offer this in the world, a full semester course on electric aircraft propulsion. I did this last semester, and I'm continuing to do it again second time, and I'm doing a video recording of this and putting it into the textbook on this, so that actually I will plant a flag for myself in this space. I mean, that's exactly what we are supposed to do. So a couple of other things, like last year and this year, I've been at the AAA Aviation Forum presenting papers on something very similar equations, like for range equation for series hybrid aircraft, where some combustion support is also provided, and the other one is actually something about deep learning for autonomous traffic control systems. So these are a couple of things that we've done, and very recently, I'm just beginning to look at, I think, in Professor Getu's videos, we had Ashok Linen's person talk about metal air batteries that are being done, and so I'm part of that little team where I'm beginning to see if we can use metal air batteries in the same way as how air breathing engines have been used, which is if I actually go faster, is it possible for me to actually improve the performance of these batteries in air, right? So that's one of those things. Technology development and entrepreneurship. So we have this incubated, IIT Madras incubated company called the E-Plane company that I have, which right now is doing something very, very small, which is like a tabletop, a VTOL and fixed wing hybrid, very similar to Lilium, which is meant for cargo transport, typically for food deliveries as well as medicine deliveries and so on. but we have plans for actually scaling it up into something bigger, which can take like tens of kilograms of payload over long distances. So it looks like a VTOL, can take off and land anywhere, and also hover and avoid obstacles in midway using deep learning and computer vision and so on, but also it can actually fly over long distances, like about 100 kilometers or 150 kilometers in single charge, carrying payload. So the long-term vision in the next 5 years would be to actually step it up to about a 200 kg payload class, by which time we think we can actually have 2 passengers go in an autonomous flight. So in the core technology, as I said, on the left-hand side, we have the computer vision and artificial intelligence. On the right-hand side, we are trying to marry the VTOL and the fixed wing in a particular way, which complements the NASA depth technology in the vertical sense for changing the airflow field around the airfoil to produce lift, so that we can now marry the two concepts together in a much better way. So we have some IP that has got generated out of that. And so the first product has these metrics. You will find that this kind of metrics are actually not really put out in the market by anybody else. That's all I have. Thank you.
Thank you, Satya. We'll come back to questions after the speakers. So thank you very much. That was awesome. Thank you. Now our next speaker is Shankar Ramurthy, and Shankar is the President and CEO of Energy Harbors Corporation. And Shankar is a serial entrepreneur. I think you've been in enterprise software, you've been in a lot of different spaces, so you've been, I think, his passion is solving really hard, big problems. So with that, let me hand over to Shankar.
Thank you. Good morning, good afternoon, everyone. So let me speak a little bit about Energy Harbors today. So we are an energy technology company, and we enable renewable energy use more widely. And I use the energy technology company because it's our energy technology that enables us to achieve real renewable revolution. In order for us to be able to be a pure renewable economy, we need to be having a very large scale storage. What's the problem? Okay. Is that good? Yeah. I can scroll it for you. And I'll thank you. So why do we need very large scale energy storage? This one. I'll just go with one conversation. Sorry, it's supposed to scroll one at a time. But, what do we have available today? We all know that we got inexpensive renewable energy, 2 to 3 cents. It's going down further. We all know it's intermittent, it's unpredictable. What do we need? We actually, if you want to really transition to a renewable economy, you need to have a cost basis of 3 cents a kilowatt hour, continuously available power. High quality, continuously available power. That's the problem. It has limitedness. So the only way that we are able to achieve anywhere near this today is by having a base fossil fuel power grid. And if you try to push up your renewable power generation, you're going to find that you're not, without large scale storage, you're going to end up dumping most of the power, as is already beginning to happen. So you hit a renewable ceiling, beyond which you cannot push your renewable power generation. And the only way in which you can use renewable is by depending upon fossil fuels to take care of the base power load and the basic power distribution. So the question, the challenge is, how do we, if we want to escape and get into this pure renewable, low cost renewable energy, highly available renewable energy, and we want to abate fossil fuel use and eliminate the glass ceiling, the solution has to be very large scale energy storage. By which I mean not the 2 hour, 4 hour, 6 hour, 100 hour storage, not the megawatt scale, 10 megawatt scale. I mean terawatt hour scale, tens of terawatt hours. Gigawatt power generation, we are actually going to be saying that we are fuel agnostic. I don't really care whether it's whether it is renewable electric or renewable gas, we are fuel agnostic. gigawatt scale, and the solution, I think you can't read like that, so I'll read what it is. It is 40 to 100 days of storage at a cost basis of 3 cents per kilowatt hour delivered. That's what we need. And that's what I'm defining as very large scale. I did a play on VLSI. I think it is very large scale infrastructure. It is also very large scale integration, because the way in which we can make this happen is with a technology that can assemble large number of components and devices and manage them in real time. So it is in fact a VLSI technology with mechanical components. Okay. I don't mean to go so fast, but just to give a quick comparison, think of this as a gigawatt plant, and you see on your x-axis hours of storage. So what you see is very quickly, as if you want to have 1,000 hours of storage, and that is because you might have extended loss of solarity for 40 days or 100 days. And what it really means is the marginal cost of storage should be practically zero. That's how you can assure yourself that you can have very large scale storage at a few cents. Right? What happens with today's alternatives is they practically, the costs start going up exponentially. If you look at all the curves, look at the green curve, that's battery. It starts going up very rapidly, even at a few hours. So it's great for less than an hour and a half. So regardless of whether it's gigawatt or whatever, that is the general behavior of battery technologies. Then you look at hydro pump storage, it is slightly better behaved, but still the costs go up, and it's certainly not affordable at 1,000 hours or 100 hours, and that's why no one thinks about it. What we are talking about is a technology curve that follows the opposite trend, that would become in fact cheaper as the size becomes larger. And then again, there's a kind of alternative. We are talking about compressed air energy storage. So it's basically taking what we have as an infinite resource, practically infinite resource, and compressing it at very high pressure, at 200, 100 to 400 or 500 atmosphere pressure, converting this basically surplus electrical energy into mechanical energy. And we store this as an isothermal compressed air. So it's almost like by using a mechanical spring. I'm taking surplus energy, taking a spring, compressing it 200 times, and when I need it, I just release it. So it's like an isothermal compressed spring. Here the spring is air. I'm compressing it 200, 300, whatever times. I'm reading out the green stuff here again. I'm sorry, I didn't realize that. We will lose the visibility here on green. Okay, so what we are really doing here is to compress air in very large reservoirs, and when you have surplus energy, storing it in these defunct, depleted oil and gas reservoirs. They are large, as you know. The minimum size of oil gas reservoir, there are many oil and gas specialists here, so you will know, it's about 40 million meter cube. Okay. So at 200 bar, you are storing about 25 kilowatt hour per meter cube. Quick math, 40 million meter cube is 1,000 gigawatt hour, which is 1 gigawatt for 1,000 hours. So that's the large scale energy storage problem. Now the question is, how do we do it? Many of you may have heard of compressed air energy storage, more in the context of many failed compressed air energy storage initiatives, right? There have been operating compressed air storage companies at scale. These are adiabatic compressed air energy storage systems that have been operating in Alabama, in Germany, for more than 30, 40 years, functioning perfectly. In fact, they are even now, I could mention Southern companies operating one of them. And, but they have never gone beyond the research stage because that technology was prohibitively expensive. And it was definitely not scalable. They operated 300 megawatt plants for about 10 hours, but its cost is like at least 10 times, if not 20 times higher than our base cost of what we need, 3 cents per kilowatt hour. The picture has got got screwed up. But it's okay. You should know the big little block. I didn't intend to block. So the basic approach to doing isothermal compression is by using proven processes. Three technology companies that tried to do compressed air energy storage in the last 10 years ended up developing new process and new equipment to solve the cost problem. And the number of cycles they took to develop the new process and stabilize it, or the cost it took to the cost points they reached with new equipment was still nowhere near what they needed to be, and they ran out of venture capital money before they could perfect the cycles. What we are trying to do is to say that we are not going to invent or develop a single new compound. We are not going to take a single new process. We are going to take at scale commercially available equipment, gigawatt scale commercially available equipment and process, so that we have no product risk, we have no technology risk. And we are essentially using an intelligent software control layer to efficiently manage these large systems. And the basic approach we are following is just water in a closed loop circuit and air in an open loop circuit. So this is a very simplified illustration of how that happens. You have the spinning pump here. The water pump on the left is pumping, is pressurizing the water at, let's say, 200 atmospheres, if that's a target pressure. We actually do it in 3 stages, but I'm just explaining the basic concept. So the water pressure is basically pressurizing water. This pressurized water is in a pressure vessel, is acting as a piston and compressing the air column in the pressure vessel. Now you would see that as you're compressing air, you would have significant temperature rises, and you're essentially cooling them and keeping them isothermal with a spray of water. So it so happens that with just 1% of the water spray, there is 1% of loss, you are able to keep the temperature isothermal. And that pressurized air is basically taken and stored in the reservoir. The large reservoir would be a depleted oil or gas reservoir. A small reservoir would be a salt cavern. Even smaller reservoir would be like a liquid air container above surface. And we'll talk about how we do liquid air, but that's something that we do in the future. But we would have different stages of the sizes of compressed air. And then you see that when we are trying to generate energy, we're taking the compressed air, driving the same water piston in the pressure vessel down, and that water piston is basically running the turbines. So this will be pumps as a turbines. Okay. So that's the basic idea. We obviously have batteries in the front to take care of transients, so that we can deliver continuous, intelligently predicted, constant availability power. It is the use of off-the-shelf components, use of a large-scale assembly of these systems that helps us bring the capital cost by a factor of 5 or more. That makes it possible for us to achieve the 2 to 3 cents per kilowatt hour. This is also very modular, so you can basically install modules for 64 megawatt is our standard module size, which itself is composed of sub-modules. And the 64 megawatt is based upon the airflow that you can tolerate without a significant loss with an existing oil gas well pipeline that goes into a reservoir. And this is modular again, so this is architecture agnostic, which means it can tolerate distributed centralized forms of renewable storage or any other form of storage. You would have as many CAES modules depending on the oil field, as many oil wells that you can install in that location. And then what you have in the green is on the other side, you would have, this could be microgrids, it could be local grids at 11 kilovolts to 110 kilovolts, distribution grids, or it could be transmission grids, or it could be a number of them. So it is grid agnostic, fuel agnostic, and architecture agnostic. So these are modules that we can insert. And who benefits from this? These are our early adopters. It's the oil and gas companies themselves that are our first customers. We are just beginning to work with some of them. We have a prototype in our lab. We have got an engineering design done, and we're just getting ready to, pilot level demonstration plants. So the value proposition for an oil and gas company is that for every reservoir, $1 that they generate from crude oil, they can have 50 times the revenue. So this is the first mover advantage for oil companies who would adopt this. And ironically, they would use their oil assets to transform into a clean energy company. It also has a few other interesting metrics. $20 billion is spent by the oil industry in decommissioning every year their existing assets. So you can basically repurpose the $20 billion towards renewable energy storage. And it produces a metric of a dollar return for every dollar investment. The benefit for an energy generator and the distributor is it increases your return simply because it lowers the cost and avoids your having to build capacity to serve peaking plants and allows you to give greater availability to consumers. And to energy consumers, to engineering companies, it obviously provides a modular, scalable, more available, lower cost system. And one of the things that we are also doing is because of this technology, it is essentially producing different functions in different configurations. Energy storage is one of the configurations. 50% of the time, your capacity is not utilized. So we use the same pressurized water, pressure vessel infrastructure to produce desalination at 1/2 the cost. Because you have pressurized water at 60 to 80 atmospheres, 90 atmospheres. You have these pressure vessels. You use existing desalination plants, the same with available technology. Don't change any technology or use whatever we have. Use the pressurized water in the desalination plants, RO membranes, to produce pure water. And 70% of the pressurized energy is recycled to produce more compressed air, to recycle and produce more pressurized water in that cycle. So that's how you have energy recycling that takes place for low-cost desalination. And for peninsular India, it's a very important solution, low-cost energy and low-cost water. And other things like cooling and other things can also be done with the same sort of system infrastructure. So this is basically what we would describe as an energy technology platform of tomorrow that is based on renewable energy that can produce multiple functions that you would need with software. Thank you.
Thank you, Shankar. Very quickly, we'll transition to our next speaker, and then we'll see how questions work before lunch. Our next speaker is Dr. Madras from IITM, both an alumni and a faculty. So he's doing some very, very interesting and important work. So I'll let him speak about the work he's doing. While he's connecting, any quick clarifying questions for Satya or for Shankar? Lots of them.
Okay. Last time you were the last one who was waiting. Yeah.
Actually, I had a question for you.
Oh, okay.
On your first page, you showed what looked like a vertical city. What was the reference? What was the vertical city? What was it? Can you please explain?
No, it was just a smart city, like a concept of a smart city.
Yeah, what's the reference? Where did it come from?
Well, okay, he's connected. Let's keep it. We'll talk about it later over lunch.
When I first was contacted, I was told I'll have to talk about affordable housing. And later the topic was changed to affordable decarbonization. I think I'm sort of a little confused what to present. So what I would do is the journey that we have taken in the affordable housing in India in a broader sense actually. And some initiatives that are taking place in the government level and how IIT is playing a role. Or you could also potentially play a role. Okay, because there are some policy changes that are taken, which can be taken advantage of all of you. what I would see is there is a mission by the government of India that by 2022 we should have housing for all. And very large amount of housing stock is really required to be built. And then you have to evaluate what are the technologies that can be used, deployed, to quickly bring it into the market. Okay. So there was, in fact, last December, there was one global housing technology challenge, where all the people around the world were called to ask for any technology. It could be construction technology, it could be the way the construction of materials, or it could be even management, whatever things that really contributes to that one is acceptable. And there's a big push for the things there. So one of the things we should recognize is India is also urbanizing. So the solutions that we require, both urban as well as semi-urban as well as rural, all the three items that we have to have. So the thing is, not all solutions will work for all the circumstances. So you have to pick and choose the right ones that are going to be there. At the same time, you want the solutions to be sustainable. That means, of course, as a building, you have to be disaster resistant, all the other features that you need to provide. But what is important here is, how do we provide, let's say, 20 million houses in the next 3-4 years? Okay, how do you do that with our labor shortage, with other capital that we have, all other things that are there? So it's an issue that takes a larger perspective. So we have a shanty towns and we have multi-story buildings there. Now, in that, I think one of the replacements that in Bombay that is being considered is to take that shanty towns that are there and they convert them into high-rise buildings for the poor, and they release the land for the others to develop, coexist with the other things there. Okay. It has been successfully done in 2-3 projects using precast things. I'll just show you the pictures a little later. So one thing is, when you're looking at the things there, one of the things that is also identified is when you are constructing for the things that for such a large thing in a shorter time, if you use technologies which use materials which take lesser embodied energy, at least even in the construction phase itself, you would save a lot of energy. Okay? And there was an organization called IFC, which is a part of World Bank. They did, for an Indian context, you can save up to 20% by choosing the appropriate technology that are existing right now that are really working in the country. So if you take those things, there are solutions available and we have to make it applicable. So if you really look at it broadly, if you really wanted to check the things there, by improving the construction efficiencies, we have based on former technologies. Okay, there are some solutions. They are based on materials, new material science, there are some solutions. So what I will do as a part of this one is, one of the things which we really worked on that one is the GFR technology. I'll spend a little more time on that one. And I'll just quickly show the things that have happened in the Indian market over the time. See, what I would show here is one example. As a formwork systems is aluminum formwork system is being used, nylon, S-form. Okay, these are the things that are being used, but they are meant for very urban things. You should have a very large number of housing clusters. Let's say not less than 5,000 to 10,000 units. Okay, only then they can be a little more economical. And there are problems. And then you can also look at tunnel form is another type of formwork systems that are there. The other things that are really being applied right now is the precast concrete technology. There's one building where we helped. It's a 24-story building for affordable housing in precast, fully precast. And then you also have a lightweight concrete construction. You also have the cold form steel housing systems meant for up to 3-4 stories. You can manage that one, and the colleague of mine works on that. So there are possibilities. Then you also want to apply some sustainability concepts in developing the housing things there. So then you have to look at whole life cycle, what is happening, what are the things that we need to do, and then take care of the things there. So I'll just quickly go through one of the indicators that we have to look at is in terms of embodied energy or in terms of carbon footprint. Okay, what are the things that we have to look at? One is in the phase of construction, the other is in the phase of operations. Most people who are working in operations, I will not touch on that one. I will just look at the things in terms of the in the construction phase and choice of materials, what we could do for the things there. I'll skip that one. The important thing that I wanted to make is as much of 20%. If you really look at the energy requirement that you'll see that one is around 2.3 terawatts. Very high things there. We can just, we need to do something about that one. So there are multiple ways this is being approached. One is to upgrade our codes where you insist in a regulatory framework. You have to do this one, there's no choice. So these concepts are brought into our National Building Code. But at this point of time, it is introduced in 2016, it is still recommendatory. It's not mandatory as yet. But I think next cycle, after 3-4 years, is definitely going to be mandatory in terms of energy use, the choice of design and the approval process, all the things. There is going to be a lot of insistence on following the sustainability design concepts and principles. I would just quickly go through one of the technologies that we worked on is glass fiber reinforced gypsum building technology, panels based on. These are the panels which are made from waste gypsum that is available as a fertilizer waste which is available plenty in the country. You impregnate with glass fibers to get the required strength, required strength. So what I just want to say, this is one factory where right now there is one factory available in Kochi, where that place alone has got 7 million tons of waste gypsum. And the country as a whole, we have around 64 million tons of it. So this is just lying waste. So if you reuse this one to a certain extent, we can get advantage associated. With this thing, we can get both. We can make both affordable as well as rapidly you can construct for the things. So my colleague was Devdas Menon, and we worked on multiple aspects of the things there. So whenever you introduce a newer building technologies, you have to codify it. So you have to do all the background work that is really required to ensure that you satisfy the earthquake design principles. You have to satisfy all the things associated with the basic design and material quality things there. We have worked on that aspect as a group, and then the other source of waste gypsum that is coming from the thermal power plants, the FGD, that's the flue gas desulfurization process. You get a gypsum associated with that one. That's also quite a bit. In fact, the NTPC alone is producing around 5.4 million tons of things. So with that basis, there are a lot of buildings that have come about. One example that I could show, before I go to that one, I just want to show what are the improvements that you're going to get in terms of embodied energy. Per square meter of panel, if you have a conventional things to this one, what is the improvements that you're going to get? This one chart basically tells you, okay, what is the embodied energy, what is the energy consumption that you're going to have for this particular, in terms of carbon footprint as well as for the things there as a conventional thing, just as a comparative thing, which basically gives you an idea of possibilities. Okay, in the construction phase itself, how much this one. There is a one building in the in IIT campus itself using PST funding as a demo building, where we also wanted to study thermal performance as well as structural as well as durability aspects associated with that one. What is important here, I just skip this one. This is just a comparison of embodied energy with respect to the thing, and also each component, how much relatively the energy, embodied energy consumption is happening. Supposing you want to look at foundation, so you can look at options. Which one works better, what type of things that you can do. So those possibilities we looked at the things. And there are a lot of studies we have done, both at a component level, at system level, comfort level, and we have to develop some, just to ensure that paints stick to that one, primers and waterproofing technologies, we have to qualify those things. So in the process, when IFC was looking at the things that they looked at it as one very highly possible thing that can be introduced. So they assembled a team. One of the things that they identified is you have to have a waterproofing there. So Dow Chemical said they'll do it quickly, but they have to struggle a lot to produce the waterproofing compounds associated. So we helped them do that. We did the test for them. After 6-7 months, they said, okay, now we have a solution, affordable solution for things. Because one way to ensure affordability is you have to have competition in different classes of problems that are there. What I would like to show here, what you have seen in IIT campus is only just a small demo building. In a slightly bigger scale, this is at the 5 hostel buildings in IIT Tirupati, where a lot of ideas were tried, GFRG construction, and also solar energy at the top, DC things, everything put together. So in one single place, we implemented all of those things, and that led to Green Building Award for IIT Tirupati GFRG buildings, and later Hardcore Design Award in the category of green buildings. Okay, so what I would like to point out here is these solutions are possible, and things that can be achieved. Okay, but there are problems. One of the problems associated with that one, how to create an ecosystem where we produce more and more panels. That's where we are stuck right now. We look at more number of ideas and investments associated with that. What I would like to jump from here, these are other things there. What my other colleagues are doing in associated energy efficient things there. A colleague of mine who is working with a company which is here, okay, he's developing for the coating systems where you can bring down the temperatures of the building. And there is reasonably successfully demonstrated this at Ahmedabad city, May 21st. The energy consumption is very large, very small after you apply these coatings. Okay, this is one example of this. The other thing where Mr. and his team is also involved is the LC3, that is the cement, where you would like to have a carbon footprint of the cement to be brought down. So they worked out some solutions associated with that one. The designs, and then they also showed around 30% of carbon emission is possible. Okay. This is just to give you a small look at some of the things in the civil engineering group that we are working in IIT Madras on the aspects associated with the things, with the housing, affordable housing. Recently, in the Government of India, Housing Ministry, Minister of Urban Housing and Housing Affairs, they are going to have an incubation cell for IITs. IIT Madras is one of them. In fact, so Oscar will be the chairman for that particular thing. That is a group. So we are going to get, that is going to be an incubation cell. It's going to have, funding will be given for an incubation cell for that one. That is immediately for 2 years. It is 5 crores every year kind of agreement in each of the IITs, 4 IITs. There are a lot of things that need to be done, and then there are some our own IIT spawned incubation ideas were there, and probably they get funded as a part of these things. So with that, I would like to end my talk. Thanks.
That's amazing work. Thank you very much for making the trip and coming out here. So, for anybody who's here looking at, maybe when you're looking at options in your career and things like that, this is amazing technology work that's going on between all those leaders who are here today, right? It's amazing. And this is the kind of work that needs to happen over the next 20, 30, 40 years. So, I would like to encourage people to engage more with all our speakers. We did run over, so lunch is outside. But I want you all to engage more, understand all this hard research, the deep research that's going on. It's great to hear the adiabatic, isothermal, all the stuff that some of you might not have heard since you left IIT, right? So anyway, it's great work. Thank you to all our speakers who made it all the way out here. Again, thank you everyone. Feel free to talk to them over lunch, and hopefully there'll be a lot more engaging discussions. Thank you. Yes. Oh, last.